Okay, we finished the naming chapter with polyatomics and then naming acids. So polyatomics are first. What the word polyatomic means, poly is several, atomic is referring to atom, so it's several atoms bound together. Many do have oxygen, so the ones that contain oxygen can also be called oxyanions. But in my class, we'll refer to these as just polyatomics. You don't have to memorize these. You've been given a blue chart that has a list of these polyatomics, but I just wanted you to notice the endings. Some have an ITE or IT ending, some have an ATE or ATE ending, and the difference is the amount of oxygen. So if there is less oxygen, it is called something like sulfite, and notice the formula is SO3 with a -2 charge. If there's more oxygen, it gets the ate ending, such as sulfate. So it's SO4 -2. So just note the difference in oxygen changes the ending of the polyatomic ion. Alright, now this is just getting practice finding these on your blue chart. So if you are following this lecture, take out your blue chart and see if you can find these. You don't have to memorize them, but you have to just have to notice where they are. So hypochlorite, ClO -1, and then if you take out the hypo and have chlorite, it's ClO2 -1. Chlorate is ClO3 -1, and I know you cannot see it here, but if you look up perchlorate, it's ClO4 -1. So just notice the hypo, ite, ate, and per prefixes and endings. It changes with the amount of oxygen. Alright, so here's some practice. Sodium hydroxide. Why does it have this formula? Sodium is Na, and it has a +1 charge. Hydroxide is OH, and I like to keep the polyatomics in parentheses. You will see why in a little bit. This has a -1 charge, so when you cross the charges, it becomes NaOH, because the ones cancel and you don't write them. NH4 is a common ion that a lot of my students cannot find because it is positive. It is the one positive polyatomic ion you have to note. It is called ammonium, and it is on your blue chart. And then C2H3O2 can actually be written in several different ways. And I wrote this way on your chart, and that is called acetate. So there's no dis or tris in this because we still have metals. So NH4 is ammonium, C2H3O2 is acetate. Okay, so there's the ammonium again. Now you will see the reason for the parentheses. If you notice the formula NH42, SO4, where did the 2 come from? Ammonium is +1, sulfate is SO4 -2. When you cross their charges, the 2 from sulfate moves to NH4 when they exchange their electrons. So if you did not have this parentheses, this would be NH42, which is not correct. Take rubidium. Rubidium is Rb +1. Peroxide, it is not just oxygen. It's O2 with a -2 charge. When you cross those, the 2 moves next to the Rb when they exchange, and it becomes Rb2O2. So careful on peroxide, that is not just oxygen. All right, a couple more. Na2SO4 is sodium sulfate, and the 2 is coming from SO4 as a -2 charge. I bring up this one, the KH2PO4. Potassium dihydrogen phosphate is actually not on your chart, so sometimes I might give you a polyatomic that you don't have, and you just have to let me know. Okay, because you don't have to look them up. You're just required to use the ones that I put on the chart. Okay, now here's some trouble. Fe and Mn, if you remember, are type 2 metals. So you see in their formula the Roman numeral. So this gets tough now. It's a lot of thinking. In my previous examples, sodium and potassium were type 1 metals, so no parentheses needed. But here these are type 2, so you do need to show me the charges. So why is this iron Roman numeral 3? Because the 3 originally came from iron in this formula. And then why is this manganese 2 hydroxide because the 2 originally came from the Mn in this formula, and you need to show that because iron and manganese have more than one charge. And then of course NO3 is called nitrate, OH is called hydroxide, and those are the polyatomics that you're learning right now. Alright, the last section is naming acids. There's an easy part and a hard part to this. But just in general, you should know that acids are molecules that make hydrogen or protons when you dissolve them in water. You recognize them by a sour taste, like lemons and limes. And there are 2 rules that depend on oxygen. So, if there is no oxygen in an acid, so check out HCl, HCN, and H2S. No oxygen means you can use hydro to begin the naming. So hydro is for the H. Cl is called chlorine, but it's not hydrochlorine acid. You need to change the INE to IC. So it's hydrochloric acid. H becomes hydro. Cn is cyanide on the polyatomic chart, but it's not hydrocyanide acid, it's hydrocyanic. So the IDE is changed to IC. H is hydro, and S is sulfur. The 2 is ignored, it doesn't become part of the name, but it's not hydrosulfur acid, it's hydrosulfuric. So add IC. Alright, if there is oxygen, it becomes a little bit tougher to name, and you have to watch the polyatomic. There's no hydro in any of these names, and you also have to be careful if the polyatomic ends in ate or ite. So, in H2SO4, SO4 is called sulfate, and why does this become sulfuric acid? Sulfate has the element sulfur, and that's where the name is coming from, so it's sulfuric, because the 8 changed to IC. This H3PO4 is called, PO4 is phosphate, and the element here is phosphorus, so this becomes phosphoric, not phosphorus, acid. In this formula, C2H3O2 is called acetate. There is no one element that stands out here, so it's not like carbate, acid, nothing like that. This is called acetic acid. So instead of acetate, you cut off the ATE and call it acetic. SO3 is sulfite, and again we see the sulfur, but it's not sulfuric, it's sulfurous because it was an IT ending. And then NO2 is called nitrite, and the element is nitrogen, but it's not nitrogen acid, it's nitrous acid, and it's OUS because it was ITE for the ending. And this does end the chapter on naming.